Please welcome Robert J. Sawyer.
It's a particular pleasure to get to introduce my old friend Lee Smolin. I've had the joy of knowing Lee for a number of years now. We run into each other at various interesting conferences and things. He is a founder and senior faculty member at the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, although he was born in New York City. And he is the author of numerous previous bestsellers, probably most controversially and famously, The Trouble with Physics. His book tonight that we're going to be talking about is Time Reborn, which actually, as we will get into over the course of the evening, is at least as controversial as The Trouble with Physics and is stirring up both lay interest and a lot of professional interest because it says something counter to what has been the prevailing paradigm in physics. Let me introduce you to my friend Lee Smolin.
Thank you. I don't see why this should be controversial. And as my mother said, the only people who will be upset with this book are people who think there are truths outside of time. But that's not hardly anybody.
Well, time is very much on my mind today, Lee, because it happens to be my birthday today. And I can think
Happy birthday.
Well, thank you. Thank you. And I can think of no better way to spend it than with a friend, having an interesting intellectual conversation. And given how much time is on my mind, and given that the first word in your book's title is time, we probably should define our terms. So to Lee Smolin, physicist, what is time?
The activity of time is the process which generates the future out of the present. How's that?
That's good. All right. Now, all right, well, let's look at it this way. We talk about, as I said, it's my birthday, 53rd birthday. So 53 years ago I was born, and all the events in the interim are fixed and done, immutable in your estimation. What about what's to come? Is Robert J. Sawyer's future life carved in stone, or is there room for things to surprise me and surprise the universe, and what is left to come?
So let's do a little bit of method here, because I'm speaking as a human being,
yes.
And you ask me what I think, and I'll tell you what I think. But the point of the book is that I used to have one answer, and I changed my mind and now have another answer.
Yes.
I'll tell you what those answers are in a minute. And the book is a recounting of the path that I took to change my mind. So I used to think, like many colleagues, that the future is completely determined and predictable from the present. And one way to recount this is Tom Stoppard in his play Arcadia had a character, Thomasina. And I won't get the quote exactly, we could be boring and read the quote in the book.
Well, we won't have to pay a permission fee if you don't quote it exactly, too.
Is he that kind of writer? But he has his character say that if one was really, really smart, or I think a modern version would be if one was really, really good at programming a computer, one could write the equation that would tell all the future from the present. And therefore, the future is fixed, and anything that the rest of your life is fixed, the rest of my life is fixed, and everybody else is here. And she goes on to say, even if nobody can be so smart as to write that computer program, the mathematics behind it must exist even if you could, and therefore it's hopeless.
Right.
Now, that used to be what was called the scientific worldview. It grew out of Newton's work and developments later of Einstein and quantum theory and so forth. I think it breaks down. It's been fine so far as it goes restricting to little bits of the universe. I think it's a fine assumption if you're controlling everything in a laboratory that you can probably get the next 10 minutes to be determined before things wreck you coming in from the outside. But I don't think that it's the right conclusion when it applies to the universe as a whole. So no, I think the future is open, and I think that this is a scientific worldview. I'm not going mystical on you. I'm not being romantic. I'm not trying to say we live in a universe which is friendly to us. But I think we live in a universe that is a lot friendlier to us than the one that Newton conceived.
Certainly when I was in high school, we were taught in physics that if you knew the momentum and direction of all particles, setting aside Heisenberg's uncertainty principle and so forth, that you could predict the future. And that I was also taught that we lived in a block universe, that it was almost like you had...
At high school, they talked
It
about
was a good high school. Oh yeah, I had a great high school teacher, George Laundrie, that almost as if all of time were motion picture film frames stacked one atop the other, and that now just happened to be the frame that was illuminated. But just because, say, you were watching Casablanca for the first time, there was no ambiguity about how it was going to unspool, whether or not, Ilsa was going to stay or go with Rick at the end, was as fixed as the moment you happen to perceive as now. And you're saying that's not, in fact, you've come around to believing that that's not, in fact, this Minkowski cube, to use the term, is not how reality is conceived.
Yes, and there are two reasons for that. One reason is that it's not enough anymore to ask, what are the laws of nature? This has been the task of science, and particularly physics, for 3 centuries, to discover what are the laws of nature. And we've made a lot of progress, especially in the 20th century and a little bit even in the 21st century. But once you know what the laws of nature are, there arises another question. Why those laws? Why the electron is there? Why are there electrons and protons? And why is the electron so much lighter than the proton? Why is the neutron just a little bit heavier than the proton? And why is there gravity? And why is gravity a lot weaker? There's dozens and dozens of questions like that are about why these laws. How did the universe choose these laws rather than different laws that we can equally well conceive of? And when you ask that question, you realize that you have a choice. You either become a mystic of one version or another, either a theological mystic or a mathematical mystic, and you say, there is some deep reason, beyond our comprehension, why those are the laws. And then you're outside of science. Or you make up some fantasy that there's an infinite number of other universes in which all the possible laws are, and we just happen to be in this one. And you're outside of science for sure. We can talk about that if anybody disagrees. Or we face the problem of really explaining in some scientific way how the laws came to be what they are. And the only possible way of doing that, I'm convinced, is if they change in time. If the laws are not fixed, if they can change in time. This was actually understood by a very smart philosopher, Charles Sanders Peirce, in the 1890s, but it took a lot for some of us scientists to begin, in this present period, to begin to think that. Laws, if we're going to understand them, they have to have a history like anything else we understand. And if they have a history, then they change, and that means you can't predict the future because they might change again.
Let's talk about a couple of things, and I want to preface this because you mentioned philosophers and philosophy, that amongst Lee's academic credentials, besides what I already mentioned, is you also have an appointment in the Department of Philosophy at the University of Toronto. I'm delighted for you. Believe me, you're a philosopher who doesn't get to ask, do you want fries with that? This is terrific.
No, really, I am very proud
it's an
because
amazing
I admire them so much. And to be admitted, usually I felt like a guest in the House of Philosophy, like you can come for dinner, but you can't stay.
And these are fundamental philosophical questions, and I know I don't want to, I'm too much of the novelist to not want to go in linear fashion as we get to the big reveal that the laws of physics you believe can change. I want to talk a little bit about something you set aside, because it's the prevailing paradigm, certainly in science fiction, is this multiverse notion right now, that there's all these parallel universes and parallel realities, a panoply of universes, and we happen to be in one of this multitude. And this idea permeated into science fiction from the realm of physics 20, 30, 40 years ago, Wheeler and so forth, 50 years ago. And now you're saying we were wrong to buy into that there in fact
What I've been saying to my friends when they start to go in that direction, I say, look, fiction is best done by professionals, and I can introduce you to one.
But it came out of the world of physics, this notion of parallel universes, multiple universes, indeed as a solution to that problem of why this one universe seems so finely tuned for the existence of complex chemistry and ultimately life.
It came from some speculation by physicists, yes.
And there's still a lot who hold on to that notion.
Sure.
Sure, and this is one of the radical ideas in the book, is that there are not concurrently a lot of alternate universes. You reject that notion.
That makes me wildly uncomfortable, because as a scientist, we can't observe them. And science is not about what might be true. We can make fantasies about other universes and tell stories, but science is not about what might be true. Your business is about what might be true. Science is about what can be demonstrated to be true from argument from public evidence.
And so because a parallel universe can't be causally related to this universe, it's irrelevant whether it exists or not.
Yes.
Yes, fair enough. But in Time Reborn, which, by the way, is a wonderful book, a lucid book. I have to do a little plug here. Give me a second to do it here.
Don't have to, but I thank you for it.
There are a whole bunch of people writing wonderful science nonfiction books these days. We have Dan Falk in the audience here, who previously wrote a wonderful book about time, for instance. But Brian Greene and others who are doing terrific books, Ray Jayawardena here in Toronto as well. This is lucid, clear, absolutely engaging read from beginning to end. And what's fascinating about it is how many paradigm busting ideas you drop in along the way. What we would call, the episode-ending cliffhangers if it was a multi-episode TV series. Because although you reject as an irrelevancy multiple universes concurrent with this one, much of your talk in this is about a succession of universes one after the next, and bringing a Darwinian notion of evolution to cosmology.
Well, that's one of the ideas which illustrates the basic theme. And the basic theme is that by considering the hypothesis that the laws of nature have evolved in the past, one can make hypotheses about how they evolved. And those hypotheses, since they're about the past, can be checked by observations of the past, cosmological observations and other kinds of observations. Now, my own history started with cosmological natural selection in the late 80s and the early 90s. And that theory made some predictions, and those predictions continue to be tested, and so far it's held up. But that's not primarily my purpose in this book, is to advance that theory. That theory is an example that you can answer more questions more scientifically by doing what would seem to be counterintuitive, which is thinking that laws are changeable in time, rather than imagining that the laws of nature are these transcendent, perfect things which live outside of time, which is what I thought for years. That's why I went into science, was to have the privilege of discovering those transcendent laws. But now it seems to me such a weird notion. If their laws are outside of time, how can they possibly act? The laws are sitting outside of time, but they're acting on every little molecule in that water glass and the ice and making it melt and everything like that, but it's outside of time. So how in the world do the molecules know that the laws are there, and how do the laws know to act on the right molecules and not the wrong molecules? Because make the glass melt, we'd be in big trouble. So I've gotten to the point where what used to be the standard metaphysical idea and standard, I think now, fantasy of my profession, or not everybody, of course, but many of us, just doesn't make any sense. How can anything be outside of time?
Right. So if the laws of physics have changed over time, that's the postulate in the book here, the laws of physics have changed, what were they before, and why did they change during the course of the existence of this particular universe?
Well, I don't think they have during the course of this particular universe. Right. And because that can be checked. There are observations of very distant galaxies, and very distant means long time ago, because it takes light billions of years to travel from there. And by those observations, we can check whether the electrons have the same masses, the same properties as they have in our universe, in our planet, and they seem to. But then we come to the Big Bang, and the Big Bang in the standard cosmology, 20th century cosmology, was posited to be, quote, the first moment of time.
Yes.
But as you marry relativity theory with quantum theory, we discover, this is my day job, is I'm trying to build on that metaphor of marrying, but I'm like the preacher that you try to marry them and they keep coming back because you didn't do a good job. But anyway, the completing the revolutions of the 20th century by combining relativity and quantum theory, we don't have a completely verified approach to quantum gravity yet, but every one of the partial approaches we have suggests that there is time before the Big Bang.
Yes.
But the Big Bang was not the initiation of the world, of the universe. It was a transition. It was a kind of big explosion. And there was some things before it. There was a universe before it. And it's natural to think that in those extreme conditions of that fantastic explosion, the whole universe kind of melted a bit and then refroze. If you see if you see the laws being fixed as like ice being frozen, then the universe, you squeeze it and heat and squeeze it and heat it and it melts and then refreezes. And in that moment of melting, the laws could have changed.
Now, this is the fundamental assumption of the book, that the laws could conceivably have had different values than they do. The ratios of electron to proton, the four fundamental forces, the ratios of their strengths could have been something different and arbitrarily are what they are. But coming back to what I was getting at a few minutes ago, there is a selection pressure that led towards this kind of universe.
That's the idea of cosmological natural selection. That's not the only idea which I've considered and which is described in the book, but it's the best.
We're going through them one at a time, Lee.
Okay, I'll have faith. We'll get there.
Yes.
Yeah.
Well, what idea do you want to talk about from the book?
No, I'm happy to talk about it.
Okay, all right. Because I mean, this to me, it's a fascinating.
I'll get. There is an idea I want to talk about from the book, but you'll get precedence.
I think we'll get there. This notion, because it goes contrary to what those of us who did not go on and do physics as a career were mostly taught, which is that these laws are immutable. They didn't have this question of whether they had any possible variance is a new notion for most people, and I think we have to take them through it a little bit, and how the selection process occurs. What I'm leading up to is what I think is the coolest idea one of the coolest ideas in the book is what the universe was selecting for, and that it wasn't for us at all.
It couldn't have been for us because we don't play a role. We don't play a role in helping the universe reproduce. So I was wondering how the laws of nature were selected, and I had a little sailboat. This was back in about 1988, 1989, and I was sailing back and forth. And a dear friend, Laura Kukas, had said I should think about this problem a little bit. And I thought, the laws are selected out of a vast catalog of possible laws, and they're selected in a particular, very unusual way because we know something interesting about the laws as they were selected, which is that they have a form. In particular, the masses of all the particles turn out to have values such that a very complex, interesting universe results. It turns out, had the laws been picked randomly, or we could just focus on the values of the masses of the particles, had they been picked randomly, the universe would be boring. There would never have been galaxies, there would never have been stars, there would never have been much around except hydrogen gas. And the whole complex history of the universe, leading to complex patterns on every scale, from the clusters of galaxies down to the molecules that comprise our cells, that universe, full of beauty and complexity, is the result of very special tunings of the values of the masses of the particles. And I wondered, how could that be? And I thought, is there a place in science where there's a process that scientifically explains how things were chosen such that a great deal of complexity results? And I thought the only place where that happens is in biology, in natural selection. So I thought, can I steal? Because in science it's very good, if there's a method that works in one problem, it's very good to steal it to attack another problem. So can I steal the methodology of evolution and apply it to cosmology? Well, what do you need? You need a universe to be able to reproduce itself. You need there to be information coded which changes just slightly when the thing reproduces itself, and which determines how well it reproduces itself. So the values of the masses of the particles can be like the genes, And how could a universe reproduce itself? Well, there was an idea already around that I could borrow from Johnny Wheeler and Bryce DeWitt, whose names you all probably don't know, but they're sort of the great pioneers of the field of quantum gravity, of marrying relativity and quantum theory. And they both, in the early 1960s, had conceived of this idea. Now, it has to do with black holes. And inside, if a star collapses into a black hole, there's this horizon that no light can get out of, but let's wonder what goes on inside that horizon. The star passes through the horizon, we can't see it anymore, and it keeps getting denser and denser and denser and denser. And what happens, according to general relativity, to Einstein's theory of general relativity, is in a short amount of time, it's crushed to infinite density. And then according to general relativity, time stops. Because the equations can't process any more information once things are infinitely dense, so the time just stops, according to the equations of general relativity. Well, according to the same equations, time starts in the Big Bang. So they had thought, maybe if you add some uncertainty from quantum mechanics, the stop isn't a full stop, it's a bounce. And so the star which had collapsed to almost infinite density explodes again. And that explosion creates something like a new Big Bang. But it's in a region of the future which we can't see because there's still the horizon around the black holes. Am I making sense?
Yes.
So we can't...
Toronto, these are bright people.
I know. I'm so proud to live here. I mean that. I'm a very proud immigrant. So there's a bounce and a new universe is created to the future of where the black hole was. And this is a method of reproduction of universes. And Johnny Wheeler had already talked about that. And he'd already talked about the laws of nature changing, maybe getting reprocessed, he called it, when that happened. So I borrowed that. And all I had to add is that the laws should change only ever so slightly, so that there's accumulation of effects, so that the child universes are very almost identical and just a little bit different from the parent universes. So then there can be selection of traits. So if we're a typical universe, then we have a parent universe, and did that parent universe have a lot of children or a few children? Well, this has been going on for many generations. And so it's much more likely that we are the child of a universe that had many children than that we're the child of a universe that had just one child. Because those universes that have many children predominate. This works just like Darwin. We are, as creatures here on Earth, we are the descendants of millions of generations of creatures that thrived and reproduced. So as a universe, we must be the descendant of many generations of universes that managed to reproduce themselves very well, better than other choices. That means our universe has a lot of black holes in it. And that's the prediction that Robert was talking about, that the laws of nature are tuned to make many, many black holes. Now, why should such a universe be friendly to us? Is that the question you're going to ask now?
Sure. Let's go with that. Yes, yes. We seem irrelevant to the process. We seem an
irrelevant to the
epiphenomenon.
process, but to get a black hole, you need a really massive star, which at the end of its life collapses through a supernova explosion, but leaves enough left over that you can't stop its collapse and becomes a black hole. So you need a really massive star. To get a really massive star, you need a big cloud of dust that's really cold. Because when things are warm, they expand. You know that. You heat up air and it expands. So if you have a cloud of gas and dust and you heat it up, it expands, so it ain't going to collapse and make a star. So you need it to be really cold, so you need a coolant. So anybody know what the coolant is? Do you know what the coolant is?
That cools the universe?
It cools the clouds of gas and dust that become big fat stars.
Wow, no.
Carbon monoxide.
My goodness.
The coolant is carbon monoxide, so you need carbon and you need oxygen. And that's why our universe is full of carbon and oxygen, according to this theory. And that's why it's friendly to life as a byproduct.
Aren't we lucky? So we have this succession. Now, where the Darwinian metaphor, what I'm going to ask you is, does the Darwinian metaphor break down? There was an origin of life on Earth, depending on who you ask, 3.8 billion years ago, 4.0 billion years ago, before which there was none whatsoever. Does this chain of ancestry of universes recede infinitely into the past, or did it have a beginning?
Don't know.
Don't know. All right.
Don't have to know. I'm a scientist. I just got to advance the subject a few steps.
Few steps, because the philosophic question there is still whether or not time had a beginning.
Yeah, and that's, there are times at any era in science, there are questions which have been answered, there are questions which are too deep to answer, and there are questions which were just ripe, which we're just getting ready to be able to answer. And up till now, we were talking about those.
Right.
But does time have an ultimate beginning is too deep, I think. So come back, which you can do as a science fiction writer, come back in 500 years and interview somebody.
I will, absolutely. Hopefully we'll have the answer for that. Well, I want to actually go back a couple of years and speak. We'll come back to the book in a minute. But to put a different flavor on things for a few minutes, you started as a physicist by reading, your interest in physics started with reading Albert Einstein.
No better.
No better, absolutely, as a teenager.
Yes.
Tell us about that, how you got introduced to Einstein before you had taken a physics course, before you'd seen a physics textbook.
Well, I was a high school dropout, but I'd learned a lot of math before I dropped out. And I got interested in architecture because of Buckminster Fuller. Does everybody know who Buckminster Fuller is? He's a great visionary architect who I had been privileged to meet. And I got fascinated by his geodesic domes, and I got fascinated by the idea of stretching them into sausage shapes and elliptical shapes, and I imagined you could take the triangles that made up the surface of geodesic domes and make any surface using little triangles stuck together. And I was a high school dropout and I needed a job. So I got this idea that I was going to design swimming pool covers made from domes stretched out, because very few swimming pools are around, so the dome would have to be stretched out. And I advertised in the newspaper to do this, and I began to do research as to how you would design these stretched geodesic dome swimming pool covers so they wouldn't fall down, because that would be bad. And the math that I needed, so I went to the public library and I started looking up the math that I needed. And the math that I needed was called tensor calculus, and I got some books about it. And it turned out that every book about it had a chapter about general relativity theory, because that's the same math that Einstein used. And so I got interested in relativity, and I went to the library again and got a book of essays about Einstein. There was this autobiographical memoir in it, in which he described why he went into science. And he played a picture of this fantasy of there being these perfect beauty and truth behind the veil of appearances, which for him was painful. He had a lot of adolescent angst all through his life. And it appealed to me. He said, life is tough and short, and your girlfriend leaves you, and your band breaks up, and things like that. But you can aspire to transcend all of this to a beautiful world of truth by trying to find the equations behind the world. And I was just hooked and off and running. Now, the really funny thing, at the end of the story, which was pointed out to me by a journalist, Dennis Overby, I didn't realize, although it was right in front of me, is that the models of quantum space-time that later with some friends we developed in loop quantum gravity look a lot like taking a curved surface, in that case the geometry of space, and forming it with lots of little triangles.
Like a geodesic dome, yes. Fascinating. So I just wanted to give people a little sense of where you got to and remind you that even if you've dropped out, you can still become a famous physicist. Einstein was a dropout too, wasn't he? And then...
I'm not sure if he quite was a dropout. Yes, he was at one point. Yes,
yeah.
And he walked from Italy, where his parents were in the electrification business, to Switzerland, and ended up talking his way into a kind of preparatory school for university.
Yeah,
That's right.
That's my recollection too. So we have this fascinating book, Time Reborn, and it postulates this notion that the laws of physics may have changed over time, actually argues that they must have changed over time. And one of the things we're taught in science class is it's great to have an idea, but your idea has to be testable. It has to make predictions.
Right.
So what predictions does this make that you and your colleagues at Perimeter or elsewhere will be testing in the years and decades to come?
Well, Cosmological Natural Selection made two predictions, which were published in 1992, which both are, it's only two, but they're both holding up to recent tests. And it would take us, they're both very indirect, but just to mention what they are, that there's one, that there shouldn't be any neutron stars heavier than twice the mass of the sun. And it was just a paper published last week in Nature measuring, because every few months or maybe every few years a new neutron star is discovered and its mass is measured. So this prediction could be violated at any time. And the mass of this neutron star is 2.1 plus or minus 0.4, which means it's perfectly comfortable with...
Just within the range.
Just within the range. The other one has to do with inflation and is, I won't mention, but is being held up by the recent observations by the Planck satellite. So those are examples.
Now, nonetheless, the book is terrific and a wonderful read, but there has been not universal acceptance of the model that is presented in the book. Some of your colleagues take contrary positions to this. How will we convince them that they are wrong?
Well, when I thought of this idea, I didn't know any astronomy really at any kind of real level. And the idea that the universe might be fine-tuned for black holes was fascinating to me, but I wanted to know, how do you test it? So I began to talk to astronomers, and astronomers were very kind and helpful. And a number of them over the years have pointed out ways in which they think the universe could be changed, the laws could be changed to make more black holes. Now, my belief, I've been in dialogues with a number of astronomers, most famously Martin Rees, the great royal astronomer, or ex-royal astronomer of England. And I believe that all those examples have been refuted up till now. And they are discussed, some of them are discussed in the book. But that's okay, because the whole point that I want to demonstrate through this example, I mean, I may be really, really lucky and this idea may be right, which would be fabulous. But it's almost as good to be wrong, because in this business of very frontier physics, it's very difficult to invent ideas which are testable. And so I would be almost as happy to find out that the idea was cleanly refuted.
Mm-hmm. The idea of the testability of issues was one of the main themes of your previous book, the trouble with physics, and as related to string theory.
Yes, yes. And there are other ideas, I want to emphasize, there are other ideas about how the laws might have changed in time, which also look to be testable. You want to ask me about one of them?
I was just going to let you go on. Yes. Give us an example of one that we could
test.
So
here's my favorite idea from the book. My favorite idea is called the principle of precedence, and it goes like this. If we do an experiment now that has been done many times in the past, we have good reason to believe we'll get the same outcome as we got in the past. Why would we get the same outcome as we got in the past? Well, one of the principles of science is that predictions of theories have to be reproducible. But what's behind that? Why can we be confident that we'll get the same results in the future that we got in the past? Well, here's the standard answer. The standard answer is there's this weird thing called laws of nature, and they live outside of time, they don't change in time, and therefore they acted to cause the phenomena in the past to make the experiment turn out the way it did in the past. And they'll be around now if we do the experiment now, and they'll make the experiment come out the same way now, and the same laws will be around in 10 years, in 1 billion years, in 100 billion years to make the experiment come out the same way. So then you have to have this mystical belief in laws of nature that live somehow outside of time and come in and act. Okay? But here's another possibility. What if every time you do an experiment, the system that you're doing looks into the past and says, are there any things like me that have been tried in the past? And if there are, let me pick from one of them what the outcome was, and I'll give them back that same outcome as was seen in the past. So there's only one law of nature, which is that nature forms habits. Nature is habit forming. And that's, I mean, I could elaborate, but you get the point. You get the point. So how could this be tested? Well, we would have to invent a novel experimental situation, a novel system that's never existed before in the history of the universe, and then it won't obey the laws that we think it should. It will just go, I don't know, and just give out a random outcome. All of these, there are much better ways to say this, much more professional ways to say this as a quantum mechanical person, but you get the idea. Okay, so are people developing in the laboratory systems that have never existed in the history of the world? And it turns out, yes, in the efforts to make quantum computers, which are computers that run according to not ordinary logic, but the laws of quantum mechanics, they are making new kinds of matter which have never existed before in the history of the universe. And this gives us an opportunity to see if this expectation that they won't obey the laws we think they should will turn out to be right. Now, I've had a lot of fun discussing this with some people who work in Waterloo. We have a sister institute for us, the Institute for Quantum Computing. And I've discussed it with people who work there and people who work elsewhere in quantum computing. And here's what they say. It's actually fascinating, to me anyway. They say, well, you know, the first time we fabricate a novel material or a novel system and we run our experiments on it, it doesn't behave as planned anyway. Because experiments are hard to do and it takes a while. It takes dozens and dozens or hundreds of trials to get the experiment working the right way. Anyway. And then once they get it working the right way, it settles down and it's reproducible and gives the answer that you would expect. So I asked them, and this is an ongoing discussion, how do you tell the difference between the system not behaving well because you didn't do the experiment right the first time and the system not behaving the way you expected because there's no precedence? And we'll see. But that gives you a flavor of the idea. If this, again, this is an idea which is probably wrong. All ideas about science are probably wrong, all new ideas. But science develops through the invention of new ideas. And again, let me emphasize, these new ideas about how the laws might have evolved, what's beautiful about them to me and what's compelling is that they're testable. This particular version, unlike the other version, if it turns out to work, we would see the laws of nature evolving in our laboratories. And that to me it's probably wrong, but if it's right, it would be a wonderful discovery. So I think that's compelling enough to look into it.
It's interesting what you said here, of course. It takes human beings to build these quantum superpositions and states that have never existed before, and they're what upset the universe from being complacent about giving out the same results over and over again. That the novelty in the universe ultimately is a human-generated phenomenon. Mm-hmm. That actually is cool. So even though the universe may be selecting for black holes, it is aided and abetted in its complexity by the existence of rational thinking beings.
Well, there are different ideas, but certainly I believe that the universe itself generates novelty. And I think that the creativity that we human beings have, that you're fortunate enough to develop to a high level in your novels, that all of us in different ways in our life are inventing, creating solutions to problems, inventing novel ideas. I think we are partaking of the ability of the universe to create novelty. So I think that the imagination is not a mirage, it's not an accident, it's not a fallacy or a fantasy. I think the imagination is a deeply important and human organ which reflects and focuses the ability of the universe itself to develop novelty.
Now, when we say novelty, just so we're clear about it, we mean things that have never existed before.
Yes.
New ideas, new structures, new patterns that are completely, A, have never existed before, and B, are unpredictable that they would exist.
Right. So I think, for example, it's not true that there's some Platonic space which exists timelessly of possible plots for novels.
Right.
I think sometimes you borrow, I'm sure, but from time to time you invent a genuinely new plot for a novel that has never existed before, and that is genuinely something new. You bring into creation genuinely something new, which then is reproduced, is published in many, many copies, goes into people's minds, and changes the future.
Which, of course, is wonderfully affirming of the human condition. One of the things that we talk about in physics class a lot, though, was that a great amount of physics and chemistry, which is a subset of physics, is time reversible. That you can't tell, if you run a film of a physical process, so to say, you can't tell whether it's running in reverse or running forward. But novelty coming into being would imply that there are detectable directionalities to time. Is that true?
Yes. And so much of life, of what we experience, what we observe, is irreversible in so many different ways. Of the birth of a child, if we spilled the water and the soda there, the unkind word said thoughtlessly to a friend. There's so many things that we do and that we experience, and our whole lives are about irreversibility. Okay? Yet, the laws of physics, as we understand them to this point, are reversible. As you say, if you take a movie of anything and you study it at the atomic level and you run the movie back, that's a possible history of those atoms. Even though it's extraordinarily unlikely, is what we have to believe.
Right. A film of somebody walking backwards, for instance, you could technically do that. It would just be bizarre that somebody was actually doing that for miles. Comedic, even.
Comedic. So, how is it that if the laws of nature are reversible in time, so much phenomena is irreversible? Well, this is a question that's been developed and thought about, and I won't tell the whole history. Some of it is in the book, from the 19th century onward. And the punchline is that the initial conditions of our universe have to have been extraordinarily improbable, according to the standard way of thinking, in order so that so much of the world is not reversible now. Had the initial conditions of the Big Bang been random, been typical, then the universe would have just been forever in what's called thermodynamic equilibrium. And in thermodynamic equilibrium, nothing much interesting happens, and nothing irreversible happens. All that happens is molecules and atoms dancing around in boring ways, and that can be easily reversed. I'm very aware there's much more to explain here, but the fact that we don't live in that boring equilibrium universe is due partly, as I said earlier, to the laws of nature being very special, and also partly to the initial conditions being very improbable, being chosen very specially. Now that's weird. How can the universe be improbable? There's only one universe, so how can it be that the one thing that exists is improbable to have existed? So I think there's a kind of problem there. And one of the opportunities, if time is really real and the laws of nature are evolvable, might be that under the laws that we think are reversible, there are deeper laws which are not reversible, and which do things which are not reversible, like bringing into being novel structures and novel laws at all kinds of levels, from the most fundamental. See, there used to be this prejudice that no laws can arise in sociology, in biology, in economics. They emerge, so to speak, but the fundamental laws are fixed. And what I'm thinking about is emergence all the way down.
Terrific. We're Time is our enemy tonight. We're going to be out of it shortly. But we do have a microphone set up in the center aisle here for people who have questions for Lee. Please do get up and use the microphone if you have a question. And while people make their way to it, I'm going to ask Lee the question a science fiction writer has to ask, which is time travel into the past possible?
You know why you're asking about the future, because I have an answer for the future.
I know. Tell us the answer to the future.
If time travel from the, well, no, actually, if time travel, no, actually, I got you. If time travel into the past was possible,
Yes.
then people in our future would be utilizing it to come to us,
Right.
and we would have met the future.
That's my thought, too, that there'd be a crowd applauding when Neil Armstrong set foot on the moon in July 1969. The tourists would have come to watch it from the future.
But that's not the science fiction question I thought you were going to ask.
What did you think I was going to ask, Lee?
What I thought you were going to ask is, if you can do an experiment and see, by it misbehaving, if it's made out of material that's really novel,
Yes.
you can tell if in the past there have been civilizations that invented quantum computers.
Yes, that's a great thought.
And you could write a book about that.
I could write a book about that, that's right. The quantum imprint on the past. I am astonished to see nobody has stepped up to the microphone here. They don't have to be hard questions. While this gentleman makes his way to the microphone, I'll just remind you that the book is entitled Time Reborn, and it's Lee Smolin is the author, and it's in bookstores everywhere, worldwide now in English. You've got a British, a Canadian, and an American edition out now. Yes, sir.
Dr. Smolin, are you suggesting that unless I can imagine it, conceive it, think it, it does not exist?
No. I'm a big believer in objectivity and I'm a realist.
Oh, objectivity? How do you mean?
I think that there is a real world out there, and it is recalcitrant to our desires and hopes and expectations and beliefs.
Recalcitrant, an excellent word for it. Is that satisfactory, sir?
Okay, thanks.
Thank you. Yes, please.
Hi. You mentioned that you dropped out of high school, and I guess I was trying to do the math on Wikipedia, and it looks like perhaps you got your PhD from Harvard at the age of 24, and I'm curious about the journey of how that transitioned.
Harvard graduate at 24, high school dropout preceding that. How did that happen?
First of all, I got really lucky. And I got really lucky in the choice of mentors several places along the way. But let me just fill in why I dropped out, because it's a little less surprising if I tell you, which is a little embarrassing. I went to a new experimental school, as was the vogue at the time, that I had actually helped start. And the first week of the school, the teachers said, we see ourselves not as teachers but facilitators, and we ask you to look around and think where in the community is the knowledge that you seek, and we will help you go out into the community and facilitate your discovering the knowledge that you seek in the city. And I went home and I thought about that, and I came back in the morning and I said, the knowledge I seek is in the university, so why am I here? So I just started dropping into classes. Without permission and all that, but it's kind of worked. Then, at that time, I wanted to be an architect to emulate Bucky Fuller. When I realized I wanted to be a physicist, I realized I had to get a real education. And I talked my way into a college, which was Hampshire College, where I discovered Herb Bernstein, who was a great teacher and mentor, without which I would have been one of those nerds wandering around the halls of MIT, dropping out again, yet again.
Thank you.
Thank you. Yes, sir.
In Troubles with Physics, there was the page where you were talking about Technicolor, and you suggested that there could be possibly that Higgs boson is made of different type of quarks.
The techniquark, so to speak.
Yes, yeah. So do you still maintain the same possibility?
The most frustrating situation has come out of the Large Hadron Collider, which is that the standard model of particle physics is verified in all the details that we can test. The Higgs seems to be there alone, a single one. It seems not to be composite, as far as we can tell experimentally, or made out of more fundamental things. There are no new quarks, there are no new forces, there's no new symmetries, there's no new nothing. So the years since the early 70s when the Standard Model was developed, there have been a plethora of very interesting ideas about what's beyond the Standard Model, and the Large Hadron Collider was built primarily for us, not to discover the Higgs boson, which we all believed had to exist, but to see what was beyond the Standard Model. And none of those ideas have been verified. There's not a bit of evidence for any of those ideas so far. That could change. And that includes, unfortunately, Technicolor. For those of you who know what Technicolor is, but it doesn't matter because there's no evidence for the idea.
Next, please. Please step right up to the mic.
Hi, last time you were here, you were talking, I asked you about Stephen Hawking and the fact that he was on the Discovery Channel saying that I believe the Americans had a time machine and he'd like to go into the future to find out if they were on the right track for string theory. And
Stephen, the only thing I'll say is that Stephen has earned the right to have fun and to have a wicked sense of humor, which he has.
yeah.
Fair enough.
Well, basically, back in 2000, when this Britannica Book of the Year, they discoveries of the year, they had a laser that was faster than the speed of light. Basically, I think that...
Not really, but that would be too technical of a discussion. It's not really faster than the speed of light.
Well, basically, that's when Stephen Hawking started to come forward with the possibility of time travel, and he wanted to get into...
Dr. Smolin has indicated that he thinks Professor Hawking is having some fun with people, and I think we'll move on to the next question.
I don't have a comment beyond that.
Yeah.
Thank you. Next, please. Thank you.
The way I understand is the universe is increasing entropy. So the black hole is the final manifestation of the largest entropy you can expect. So how does it condense into some small little thing, become very highly small entropy, and then expand again?
You're asking how a black hole gives birth to a
How that
universe.
cycle reverses itself? I just want to understand a little bit. Is it?
I don't think that I'm aware that to give you the full answer, I would spend 5 minutes boring most of the people in the audience. So let me just say I don't think that's an issue, and if you'd like to discuss it, I'm happy to discuss it.
Thank you. Very good. Are you standing in the queue there, sir?
I guess I'm looking and thinking about the Higgs boson and dark matter now. In your opinion, is there dark matter, and does it matter?
Thank you. It would be very romantic if the explanation for the dark matter were that there were no dark matter and instead the laws of gravity were different on the scales of galaxies and clusters of galaxies. That's a set of ideas which to a theorist is more attractive, is more romantic because it's more fundamental than just there's another particle which happens not to have an electric charge that we've missed. But I have to say that all the attempts to make good on this deeper explanation have not been impressive so far. Although there are some small, there's an idea called modified Newtonian dynamics by somebody called Milgram in Israel, which goes some way towards covering the phenomenon that galaxies seem to have extra matter in them. But the idea, when extended, does not seem to hold up completely. So it looks like dark matter is the most parsimonious hypothesis. On the other hand, it hasn't been discovered either. So the jury is out.
So a lot of physics to be done. Sir?
Yeah, I got the new book from the library yesterday, and I jumped ahead thinking if you thought time was real, Professor Smolin, how you would deal with Einstein's views that it wasn't. And and you're going to have to alleviate all my confusion, but it seemed like you were changing the relativity of simultaneity with a relativity of shape. So that got me thinking, gee, if in the twin paradox, if my twin roared away and came back at the speed of light, would he come back not younger than me, but a different shape? How, does
A
design...
different size. It's a relativity of size.
And how does that, so the stuff that Einstein said about time being relative and everyone, us all carrying our personal clock, all of that is, on this theory, not the case?
It is all the case. It's a different way of, so again, this will be hard to do justice to in a minute, but rather than thinking that clocks can arbitrarily slow down and speed up, there's an alternative understanding of the same theory of relativity, so it makes the same predictions, by Julian Barber and some young colleagues, called shape dynamics. And the idea is that rather than time being relative, size is relative. And you could move something around and it might come back and appear to be a different size, rather than have a clock that ticked a different number of times. Now, they're actually the same thing. And a way to see the same thing is to think of a clock made of a box with mirrors in it. And the tick-tock is a photon of light bouncing back and forth between the mirrors and the walls of the box. And if we shrink the box, the light is going to bounce more often and the clock is going to speed up. And if we expand the box, the tickings are going to be less often and the clock is going to appear to slow down. So the same phenomenon of time appearing to speed up or slow down can be described in a different way, in which the sizes of things are changing arbitrarily. That just gives you a taste. There's a lot more to say about that. But that gives you a taste of how. So in Einstein's version of the theory, size is fixed, but time is relative. In Julian Barber and young colleagues' version of the theory, time is fixed, and I need this for time to be real. So there can be an objective meaning to the distinction between past, present, and future, but size is relative. And it turns out to be a reinterpretation of exactly the same physical theory. And it's in chapter 14, I think.
Good evening. I want to make a brief diversion to the questions of philosophy and science. I have a good friend who almost wanted to be here tonight. He did a science of philosophy degree. And I was also very nearly myself at an event with Lawrence Krauss, who's gotten in a bit of trouble for disparaging philosophers. And I know you do both worlds, and I know physicists have a lot of stuff to say about philosophers. Stephen Hawking got in trouble with it in his recent book, and so did Krauss. And do you, when you're in the philosophy faculty, get anything disparaging about being a scientist? And if you do you just sort of shrug it off because we really shouldn't care what the philosophers think?
I think there's a lot of unfortunate disparaging of things that you don't understand. This is a very common human trait. And my view is that science, when we're asking the most fundamental questions in philosophy, are very closely related. And we're related through a history which joins them. So people like Newton and Leibniz, Descartes, were not either scientists or philosophers, they were both. And I aspire to be in that tradition. And I think that I'll quote somebody that for me was a great role model, David Finkelstein, a great theorist, physical theorist, who, by the way, was the first person to figure out what black holes really were and how they work. And David likes to say that if you want to make a leap, a conceptual leap, dealing with the most fundamental issues, you need a running start. And the way to get a running start is to go back in history and philosophy and know what people have thought in the past about the question that you want to make a leap with respect to. So I think, Lawrence Krauss is a friend. He's highly articulate. He's played a very important role in the wars about evolution and creationism in the United States. He's a very articulate spokesperson for science, and I think that he overreached himself, and I'm also aware, I mean, this is his hometown and he's often here. I think that was an unfortunate book, and the controversy that stemmed from it was unfortunate. And it was just, I mean, he's somebody who's done many important things. It was not his best moment. And the kerfuffle that arose from that, I think, was unfortunate on both sides. I mean, I've heard, just to answer your question, I mean, I've heard philosophers say silly things about scientists and vice versa. But there really is a connection between them. And this gives me the opportunity to mention that the book is dedicated to a philosopher, Roberto Mangueira Unger, who is a deep thinker and one of the most ambitious and large thinkers alive today. I'm happy to take the opportunity to make him be better known because he's not nearly well enough known in the English-speaking world. He's a Brazilian who teaches also at Harvard Law School. And he, for reasons completely of his own, had come to the view that laws of nature must have evolved. And we were introduced by a mutual friend, also a legal theorist, Drusilla Cornell, and began a conversation 7 years ago that pushed me and inspired me on this journey that this book reports, and the book is dedicated to him. And those who want more after reading this book might be interested to know that Roberto and I do have a book which is going to be a lot tougher of a read than this. This I worked on very hard to make it communicate to the widest possible audience. The book with Roberto, I'll just quote the level of his ambition. I say to him, Roberto, we should make this more accessible. And he says, but I don't expect to be understood in my own time.
Well, one of the beauties of this book is that it is easy to understand. There's not a single equation in the book. And I want to read a quote from the back cover from Jaron Lanier. Did I say that right? Lanier?
Good enough.
Close enough. Jaron Lanier, who wrote one of my favorite books of recent years, You Are Not a Gadget. And he said of this book, Time Reborn, from Knopf, Canada, Smolin provides a much-needed dose of clarity about time with implications that go far beyond physics to economics, politics, and personal philosophy. An essential book for physicists and non-physicists alike, Time Reborn offers a path to better theory and potentially to a better society. Lee, I want to thank you so much for coming and sharing your a little bit of your personal history and some of the insights that are in this book. I commend it to you. It really is a fantastically enjoyable and lucid read. My name's Robert J. Sawyer. This is Dr. Lee Smolin. This is the Appel Salon at the Toronto Reference Library. Thank you all for coming out tonight. Lee, what a pleasure to spend my birthday with you. Thank you.
Thank you, and happy birthday.
Thank you so much. Thank you.
Thank you so much.
Thank you.